Hi everyone, welcome back to my YouTube channel. My name is Jande Nyanwi. I'm a graduate student at Carnegie Mellon University, Africa. Today we're going to learn about transformers. Transformers were introduced in Attention is All You Need paper in 2017. This is one of the famous paper, and the introduction of transformers or the invention of transformer is one of the greatest invention in AI in the last decades. Transformers were initially introduced for machine translation tasks in 2017, but they have quickly become default architecture in other modalities beyond natural language processing. So the outline of this video is going to be like this. I will start looking at neural network architecture before transformers. I will also look at every component of transformer architecture, such as attention. Also try to visualize attention mechanism. Also learn about large language models which are inspired by transformers. Also look at some popular implementation of transformer architecture. I'll also look at the state of transformer today. I'll also look at efficient transformers. I'll also end the video with some amusing transformer tweets. And then there are some option exercises if you want to dive deep into transformers. Most of this video is centered around sequence modeling, even if we might talk about other modalities. There are basically three ways to process sequential data with deep learning. The first approach is to use multimodal perceptron or MLP. The second approach is to use 1D convolutional neural network or 1D CNN. And the third approach is to use recurrent networks such as RNN, LSTMs, or get recurrent units. All of this is to motivate transformers, and we're going to talk about each approach in detail. Starting with multimodal perceptron or MLP. MLP are a sequence of linear or fully connected layers that goes from inputs to outputs. When it comes to sequence modeling, MLP are not preferable due to a number of reasons. The first is because of their feed-forward design. They can't preserve all the information in a sequence. So MLP basically take things in a feed-forward fashion from inputs to outputs. They cannot reason about the order of information they are processing, and they also take many parameters. The second approach is to use convolutional neural network. Convolutional network or convolutions are a kind of neural network architecture that can process image and other modalities such as sequential data, like you are seeing. Convolutions have so far been successful in image recognition, but not quite successful in sequence modeling because of many reasons. The first is that although convolutional network can be parallelized, which means they work well on modern GPUs, they require many layers to be able to capture long-term dependencies or to be able to handle long-term dependencies. The third approach is recurrent neural network. Recurrent neural network or RNN are designed for processing sequential data. In theory, RNN can handle or can model any sequential data, but in practice, they are not capable of handling long-term dependencies due to unstable gradient problems. LSTMs or long short-term memories are a version of recurrent network that can handle long-term sequence. LSTMs have steady states or the horizontal line that we are seeing on this image, and the gates that control the information flow. We are not going into details of every architecture, but LSTMs are one of the most used recurrent networks, especially in sequence modeling. LSTMs work great in practice in most sequential modeling program, like you are saying. And there are many other versions of LSTM, such as get recurrent units, which people say which is much compute efficient than LSTM. LSTMs work great, but not quite enough. So there are too many problems of recurrent networks. The first is recurrent networks are designed to process one token at a time. They, in other words, process things in series. And our modern accelerators, or say let's say GPUs, are designed to process information in parallel. So then recurrent networks are hard to scale. Recurrent networks are good at preserving the order of the sequence they are processing, but they cannot reason about the global context of the sequence. For example, in machine translation, a task of translating one language to another, the context of sentence being translated is as important as the order of the words in the sentence. So it's really not just about the order, because the context matters as well. Then the problem is, how can we design neural network architectures that can reason about global context and be parallel at the same time? Or are there any neural network architecture that can reason about the global context and be parallel at the same time? So the question we are trying to answer bring us to transformer. Transformer was introduced in 2017 in Attention is All You Need paper by Vashani et al. Attention is All You Need is one of the famous paper nowadays. I want to read a half of abstracts because it conveys a lot of information about why we really need to have architecture like transformers. So the dominant sequence transduction models are based on a complex recurrent or convolutional network that include an encoder and decoder. So what they're saying here is that most models before transformers for processing sequence were usually structured into encoder and decoder, but they're all made of either recurrent networks or convolutional network. The best performing models also connect the encoder and decoder through an attention mechanism. We'll see an example of this, what they meant. Um, so we propose a new simple network architecture, the transformer, based solely on attention mechanism dispensing with recurrency and convolution in theory. So this paper proposed a new neural network architecture called transformer, and this transformer is only based on attention mechanism by ignoring some few layers that are used. And this transformer does not rely on any recurrent or convolutional networks. So a transformer, like we saw with the neural network architecture, that's the first thing. This architecture can process sequential data such as text, audio, and video. It also has shown to work well in other modalities beyond sequential data such as image. A transformer does not use any recurrent or convolutional layers. Its principal layer is called attention, and it also contains other basic layers such as fully connected layers, normalization layer, embedding layers, and position encoding layers for maintaining the order of the tokens. Original transformer was made of two parts. The first part is encoder, which is on the left side, and decoder, which is on the right side. Transformer is an autoregressive architecture. What I mean is that it generates one token at a time until the whole output sequence is generated. And this transformer was basically used to predict the next token. So the token to be predicted is conditioned on all previous generated token. This is what autoregressive mean. The current token to be generated is conditioned on previous generated token. And this is encoder. So encoder is one of the main building block of transformer that transform the input sequence into a compressed representation. Encoder is repeated 6 times. Each block it has 3 main layers. There is multi-head attention, there is layer normalization, and there is MLP or feed forward. Multi-thread attention and MLP are referred to as sublayers in the paper. So between sublayers, there are layer normalization and dropout, and some residue or skip connection in between. So the more number of encoder layers, the larger the better the model, and many layers help the model to capture the global context of any input sequence. Or in other words, the more layers you have, the better your model can learn a better representation. Decoder takes the output of encoder and output sequence and predict the next token. Decoder has same layers as encoder except additional multi-thread attention that is that operate over the output of encoder. So the safe attention used in decoder is masked to prevent the current token from attending to previous token in the output sequence. So if the decoder has a full access to the to the whole output sequence, this would be cheating, and it would result in model that is not robust enough, or model whose generalization is not good enough. So the layer in decoder are also repeated 6 times in the original transformer, and this is a hyperparameter to change. So in recent large language models, it's beyond 6. It's multiples of 6. Original transformer had encoder and decoder structure because it was introduced from machine translation. A machine translation is a sequence-to-sequence task, so the input and the output are both sequence, as opposed to tasks like classification, where the input is a sequence, like image being treated as sequence of patch, or text being treated as sequence of token, and the output is a category label. So transformer in basic classification task typically use encoder or decoder, but not both. Something to say here is that in most computer vision tasks like image classification, people normally use encoder, while in most language tasks, people normally use decoder. So like GPT-3, for example, I use decoder. VIT or vision transformer, I use encoder. But that's basically it. So transformer is the way to look. So the way to look encoder and decoder is because it was introduced for machine translation, a task that demands to process input and output all being long sequence. Attention is the main important element of transformer. So attention is this mechanism that can provide the network the ability to focus on the most important part of data and to not focus or to pay less attention to the rest of the data. So attention is this really just attend to key features in the data. Attention, you might think that attention was not a thing before transformer, but it's really not the case. So people used attention long before transformer. There are a number of work which try to use attention in the computer vision and natural language processing, but let's start with the one in computer vision, specifically in image captioning. So in the paper show attend and tell neural image caption generation with visual attention, people used attention to focus on the part of the image when generating the caption. So as you can see in this image, on the first example, a woman is throwing a frisbee in the park. You can see the network can be able to focus on the part of the image that has lots to do with the caption. For example, in this particular caption, you can see that the network is focusing on the frisbee than other parts. Another example is a dog is standing on a hardwood floor. So you can see that the network is focusing on where the dog is rather than focusing on other part of the image. It also goes the same as the next example. So a stop sign is on a road with mountain in the background. it's pretty clear that the network is being able to realize, hey, this background doesn't matter much. The stop sign is what matter in this caption. Another example is a group of people sitting on a boat in the water. So a group of people sitting on a boat in the water, the network is able to recognize that a group of people is the most important part in this image. And you can see that clearly. So this was in the computer vision, and there is another example in natural language processing as well, especially in machine translation. So people try to use attention along with recurrent networks to give the network the ability to listen about the context of the sentence being translated. So in this example, it's English to French translation. The input sentence is the agreement on the European Economic Area was signed in August 1992, and its corresponding French is l'accord sur la zone économique européenne a été signé EAU. Sorry, I don't know French, so but you can see that. So what we see here is diagonal attention mean what correspond in the order. So the network is being able to recognize that this particular word from English to French, they have to be in the order they are in. Like their order is the correct order. But if you go to zone économique européenne, the target translation in French, you can see that the network was able to figure out that when translating European Economic Area to French, it goes the other way around. So this is a really beautiful demonstration of how attention is just powerful. Like it's able to not just capture the order of things, but to also listen about the global context of the sentence being translated. So intuitively, attention is just focus on the most important part of the data. But technically, attention measures the similarity between two vectors and return similarity score. This similarity between two vectors is computed using dot product. Mathematically speaking, when computing similarity between two things, we normally use dot product. So a standard attention takes three main vectors: query, keys, and values. But what are queries? What are query, key, and values? Query, key, and values are established terms in search engine and database system. If you have been working in database, for example, you probably know query, key, and values. So to understand those terms, let's take an example. So imagine you're trying to search articles that are related to AI and healthcare on TechCrunch. So your query is what you put into the search box on TechCrunch. So your query is AI and healthcare. Internally, TechCrunch organize articles by set of predefined keys. So keys might be biotech, fintech, energy, tech layer, social media, autonomous driving, etc. And so your query in healthcare is going to be compared to the predefined keys, and the search result will show articles that match with your query and keys. And for example, so in this particular example we are taking the search result that we see are the top articles that match with your query. It's not all articles, it's the top articles which match with your query. And the values in these examples refers to all articles in the database. As a disclaimer, this is an example. I'm not attempting to show how TechCrunch search system works. So we said the attention layer take query, key, and values, and then compute the dot product or similarity between query and keys. Apply softmax to the product of query and key to get probability distribution of the dot product, and and also apply the result to get the weighted sum of the values. So in a few words, attention computes similarity score between query and keys, and then weight those score with values to produce weighted values. So attention, this is how it's represented mathematically and graphically. So you basically have you are multiplying query and key. It's multimodal or matrix multiplication. You are scaling them with square root of dk. So this dk is a scaling factor, and the reason why it's done is because the dot product of query and keys can become too large and hence can result in unstable training. So dividing the dot product with this square root of dk help to alleviate the numerical instability issues. And then after scaling, you are putting everything into softmax. Softmax, as you know, give the probability distribution, which all add up to 1. And after softmax, you multiply it with the value. So you multiply the probabilistic the probabilistic score with values. The masking is optional because it's only applied in the decoder part of transformer. So computing attention is pretty fast. So as you can see, there is no recurrence, there is no loop, there is no convolution. It's just two matrix multiplication. The only bottleneck is quadratic time complexity, which is introduced because every token has to attend to other token in the sequence. So, but as the paper shown, this is not a big deal in machine translation, since input sequence being translated from one language to another are typically short. All rest to say they are not very large. This is attention in as Python function. So it's imagine it's like a function taking three main inputs: query, key, and value, and some additional input like mask and dropout. So the first thing is to get the size of the query vector and to find the similarity score, which we get by computing the dot product between the query and key, and then we scale the result with square root of dk to alleviate instability or numerical instability problems. And if mask is not none, we apply mask, but this is done in decoder. And then after computing the similarity score, we apply softmax. Softmax gives us probabilities which all adds up to 1. And if the dropout is not none, we apply dropout, and then we return the similarity score in probabilities are multiplied to the values. And then you have this attention. So it's pretty simple, it's expressive, it's straightforward, it's fast, and it's maybe that's why it's been working well in most modalities, as we've seen in the later part of this video. So attention is permutation invariance. This is because if you try to change the order of words in the input sequence, it doesn't affect the output. Permutation invariance in attention is the result of dot product between query and keys. You might have hit multi-thread attention and wondered what is multi-thread attention. Well, multi-thread attention is nothing other than multiple attention layers that are concatenated together to provide a single output. So combining attention layers help the model to learn better representation than merely using a single attention layer. Original transformer paper used 8 attention heads, but this is a hyperparameter to change. Recent large language models that use transformer, they have more than 8 attention heads. Another thing to note is that it's called self-attention when query, key, and values are derived from the same source. Otherwise, it's close attention, especially when query, key, and values are different. Transformer, beside attention, which is the main component of transformer, it has other layers. The first one is embedding layer. Embedding layer are right at the input of transformer. So embedding layers take the input sequence, and then they convert the input sequence into dense token. So this is the code snippet of embeddings. So it's from PyTorch, and this code is taken from an annotated paper by Hang et al. So embedding is just a simple layer in PyTorch, which is also available in Keras. And this embedding take the vocab and D-model or dimensional model, and this dimensional model is maintained across the whole network. A dimension of the model is also referred to as width of the model. And this, after computing the embedding, we also multiply the weights by the square root of D model. And another layer is positional encoding layer. Positional encoding layer is really important thing in this transform architecture. This is because attention has no clue about the order of token. So attention, and this is because attention does not use any recurrence methods. So it makes sense then to have some ways of maintaining the position of token in the sequence. The order of transformer I used a sine wave and cosine function of different frequencies to maintain position of token. But in the paper they show other approach they took, and they tried to show the results of the performance of this thing when using position encoding layers, the performance of this thing when not using positional encoding layers. But what they found is that using position encoding layers improve the performance, and that makes sense since attention has no clue about the order of the token. In the previous part of this video, we saw that attention is permutation invariant, so it really has no order of the things. If you change the order of the token, the output doesn't change. So we really need to keep the order of things, and this was done using position encoding layers both at the encoder and at the decoder. Another important layer in transformer is layer normalization and dropouts. So transformer use layer normalization since it's been working well in most novel papers. Layer norm keep the activation of layer in optimal range, and it improves the training stability as well. You might know batch norm or batch normalization, but batch norm is rarely used because it has different behavior between training and test time, while layer norm have the same computation between train and test time. Another thing to notice is that layer norm is applied independently to each position. Dropout was used as regularization technique to avoid overfitting and to improve generalization as well. Dropout is inserted after each multi self-attention and fully connected layer, but it is before layer norm. It is also applied to the output of position encoding and input embedding or output embedding. Residual connection are also one of the most important part of the transform architecture. In fact, the residual connection are a norm today in almost any model. So residual connection facilitate the flow of gradients, and they prevent vanishing gradient problems. So in particular, residual connection or skip connection are used to carry positional information to higher layers in transformer. This is what is shown here. You can see that with residuals, we have a smooth information flow over the layers. So as we go deeper into the architecture, we have a smooth information flow because of using residual connection. And this is not the case if you remove them. If you remove them, you can see it doesn't look good. Another important part of transformer is fully connected layers. So transformer use many fully connected layers or linear layers in both encoder and decoder. In the original transformer architecture, all fully connected layers were followed by Reru nonlinear activation. The paper also use the term feed forward, referring to MLP. This is the code snippet of the feed forward layers. So it's two linear layer, they maintain the same shape. So the first layer take a dimension of the model as the input shape, but you can see that the second layer also its output shape is dimension of the model. So all these layers they maintain the same shape, and also you can see that dropout is applied right after this feed forward broke. All MLP layers are independent, but they are identical. Like they are the same, but they are independent. Another way to say it is they are applied to each position independently. A recent transformer models such as BERT, GPT-3, and VIT use Gero or Gaussian error linear unit instead of using Gero. You see that most papers today are using this GRU activation. And now that we have seen what we have tried to understand attention, let's try to visualize it. So attention has the ability to learn the global context of the sentence or the sequence, and some attention heads can tend to distant word in a sequence, which explain why attention alleviate long-range dependencies. So this is a great tool from Hugging Face Expert, which you can use to try to see how words attend to words when fed to attention layer. So I invite you to experiment with this tool. The last time I used it, it was open and easier to use. You can put your custom sentence, and then you can change number of layers, number of heads, and then you can see how words attend to another words. Another really great tool for visualizing attention is called BERT. So here this is a head view which shows attention for one or more attention head in the same area. You can see that this is the first layer, but you can see that how words attend to other words. This BERT really shows how things change in the attention layer. So this is a model view which shows the bird's eye view of the attention across all layers and across all heads. Something to say here is that in the ear layers and in the first heads, one thing you can see is that the words, every words attend to all other words. But as you go deeper into the architecture, as you increase layers, as you increase heads, the words start attending to relevant words than attending to everything. And this makes sense since the whole goal of attention is to just attend to the most important part of the input data. In the sequence perspective, the whole idea of attention is to attend to words which are relevant than others. This is neuron view, which shows or which visualize individual neuron in the query and key vectors and show how they are used to compute attention. If you are finding it hard to understand, I invite you to play with this tool, and I have also added some extra resource for understanding visualizing attention mechanism. So there's this BERT paper which goes along with the repository that gave those visualization, and there's also interactive notebook that you can play with. And there's also a really nice blog which explains the inner working of attention. So now that to understand the transformer architecture, let's look at large language models or LLM, which are inspired by transformers. Before transformer, there was no such thing as large language models. So since the introduction of transformer in 2017, language models has got bigger and bigger. The first transformer had 65 million parameters, but today language models they have hundreds of billion of parameters as we see. So again, transformer base had 12 layers. So 12 layers it is basically to say 6 encoder and 6 decoder. So layers are a number of encoder and decoder layers. It also has 512 width or the dimension of the model and 8 heads. Remember that heads are the number of attention in multimodal self-attention. And this transformer base had 65 million parameters. GPT-1 is one of the earliest big transformer, and GPT-1 was from OpenAI. People at OpenAI have really remarkable history in large language models. So there is GPT-1. GPT-1 had 12 layers, the same with transformer base and 12 heads. And this GPT-1 had 117 million parameters. BERT large was also one of the earliest large language model. BERT had 24 layers, double the width of GPT-1 and 16 heads, and BERT large had 340 million parameters. XLNet large had 24 layers, the same size or the same width as BERT large, and the same head as well, and the same number of parameters. Roberta is also another large language model which had 24 layers, the same size as Beta and XNet large, and also the same heads as well. But Roberta had 355 million parameters. It might be that the dimension of other layers were different, which is not reported here. And GPT-2, which is direct scale up of GPT-1, had much many number of layers. So GPT-2 had 48 layers, 1,600 width or dimension of the model, and the number of heads is 48 in GPT-2. And GPT-2 was one of the really large language model. GPT-2 had 1.5 billion parameters. As you can see, it was 10 times even higher than all previous models. And also Megatron from NVIDIA had 72 layers. It also had 3072 width and 32 heads and 8.3 billion. So Megatron was designed that people at NVIDIA. So it makes sense. NVIDIA design computes, they design GPUs. So they say, hey, we design the GPUs that are used to train this large language model, so we can scale these things up to 8 billion parameters. But then OpenAI followed up with this Turing energy, which had 17 billion parameters. And then people at Google, they said, hey, we have been at the forefront of these things. We are the people that design transformer. So we can double these things. We can scale these things up to 137 billion parameters, and they designed Lambda. People at OpenAI said, hey, we are the first people who released generative pre-trained transformer. So you can't really beat us on number of parameters, and they designed it GPT-3, which is one of the famous large language model today. So GPT-3 had 96 layers. 12,228 width or dimension of the model. GPT-3 also had 96 heads or number of attention layers in multi-thread self-attention. And total GPT-3 has had 175 billion parameters, which is pretty huge. But then Gopher, which is from DeepMind's, increased GPT-3 a little bit. So they say, hey, we are still here. Like we can add 100 billion parameters to this thing, and they designed Gopher which had 280 billion parameters. Recently, people from Google, they designed Palm or pathway large language models, which had 540 billion parameters. So as far as I know, today, Palm is one of the largest language model, but there are rumors that we might even see GPT-4, which will be in trillion of parameters. But it's very early to say. But one thing to expect is that this large language model will keep increasing. They will keep getting bigger and bigger, and hopefully they'll keep getting better and better. And that will be a nice thing, because large language models are really powerful. And as people say, like by scaling all these large language models, it's hard for most people to make use of them because they are really hard to deploy. But if they are better, they can help us to solve a complex problem. They can help us to solve mathematical problems. They can help us to synthesize really beautiful articles. I'm not saying that you should use GPT to write articles, but I really think that there are many ways that we can use these large language models, and I'm very optimistic. So large language models are usually trained on massive unavailable datasets from the internet through technique called unsupervised pre-training, and they are then fine-tuned on NLP downstream tasks such as text classification, sentiment analysis, question answering, and summarization. So this is a summarized workflow of how most people use large language models. So all these big or large research lab, they collect data from web. So that is social media conversation, that is GitHub code, books, news, Wikipedia. And then they feed all this data, all this massive data set to a transformer, a very large transformer. And then at the end, they fine-tune on downstream tasks like classification, summarization, and question answering. During fine-tuning, the dataset used are pretty small, so you might see a classification dataset of around 10,000 samples also. Also, modern large language models are zero-shot or few-shot learners. So few-shot learning means using few samples to perform inference on a particular task without fine-tuning. So in few-shot, you just need few demonstration of the task, and you don't need to collect fine-tuning datasets. In zero-shot learning, you don't need any sample at all. So you can just prompt the model, and the model can do whatever you want it to do. You can tell it to summarize a particular document, you can tell it to complete the missing word, and that's it. The model just does it. I will see on this later, especially looking at GPT-3, because one of the models that showed that large language models can actually perform few or zero-shot learning. So let's now look at BERT. BERT stands for bidirectional encoder representation from transformers. BERT is one of the earliest language model that shown that it's not only that you can pre-train these large language models, but you can also be able to fine-tune them on downstream tasks, which is what people care about often. So most people doesn't care about having these billion of parameter models. Most people want to use those models in production, but it's very hard to train them. Like it's very hard to train them. It's very hard to deploy them. So what most people care about is being able to fine-tune those models on downstream tasks. And this was shown by Bates. So the key idea in BERT is to pre-train deep direction transformers on very large and reliable datasets, and then fine-tune on downstream tasks by only adding one additional layer, which depend on the task we are performing. So example of downstream tasks that you can perform with BERT are question answering, sentiment analysis. And when BERT was introduced, it built most state-of-the-art on NLP benchmarks. So BERT pre-training was to what ImageNet pre-trained models were and still to computer vision. So in computer vision, what people mostly do is we take a very large model, let's say Convenext, it's the latest one, or any other models like EfficientNet or LazyNet, and then you pre-train that model on ImageNet usually, and then we fine-tune on smaller data sets. So you can pre-train on ImageNet and fine-tune on CFAR10, for example, or CFAR100 or MNIST. And always fine-tuning a pre-trained model work well than training from scratch. So in language words, BERT was the first, or let's say one of the first papers that showed that you can pre-train these large language models and then fine-tune them on downstream tasks. So prior large language model pre-training technique like GPT-1. So prior language pre-training models like GPT-1, they relied on task-specific architectures and were unidirectional. So unidirectional, that is to say they operate left to right, and that means that each token can only attend to previous token. BERT used masked language models. The idea of masked language model, as we see, is to randomly mask some token in input and predict the vocabulary ID of the masked words based on the context of the sequence. And by doing this, BERT achieved bidirectional pre-training. BERT is unified architecture, so the same model that is used in the pre-training is the same as the model that is used in fine-tuning. The only difference is in the fine-tuning where you add one additional layer depending on the task we are performing. Also, self-attention used in the BERT is bidirectional. So in models like GPT, self-attention is indirectional and it's constrained where every token can only attend to previous token. In particular, models like GPT, they use decoder, part of the transformer, and as you saw in decoder, the attention is masked, so which means you can only attend to previous token, and that makes the whole model unidirectional. And by BERT, it's use encoder. So and then this encoder, every token can attend to all other token. There's no constraint. But there is a problem with bidirectional attention. So because each token can attend to itself, I mean, if every token is attending to every other token, then there's a possibility of each token attending to itself. And this can result into a problem. It can limit the generalization capabilities of the model. So to alleviate this, BERT used a masked language model pre-training approach, where, like we said, they randomly masked some words in the input sequence. They said they masked 15% of the input sequence, and then they predict those masked words. So another pre-training approach used is next sentence prediction. But this was a rough overview of BERT. So if you want to learn more about BERT, I recommend you to read BERT paper, which is one of the really good written papers. Let's now go to GPT-3. So GPT-3 is one of the famous large language model today. I think nowadays everyone knows GPT-3. So GPT-3 was introduced in the paper Language Models are Few Learners from OpenAI. So pre-training on large and labeled dataset and then fine-tuning on small downstream dataset is not enough. So the claim was that we human, we don't need to be shown 10,000 of samples to perform a particular task. Sometimes we need few samples, or sometimes we don't need any sample at all. So people at OpenAI try to design language model that can perform new tasks without requiring to be fine-tuned, without requiring you to correct fine-tuning datasets. But the kind of the model that can only be prompted by few samples or no samples at all. So GPT-3 is 175 billion parameter model. It's a direct scale up of GPT-2. Like we saw, GPT-2 had 1.5 billion, and GPT-2 was a direct scale up of GPT-1. So without fine-tuning and without performing any gradient updates, GPT-3 can translate from one language to another. GPT-3 can answer a question that it never seen. GPT-3 can summarize text content such as books. GPT-3 can generate poem, and GPT-3 just removed the need of correcting large labeled fine-tuning datasets. GPT-3 can perform any context learning. So the idea of any context learning is to give the model the ability to learn a wide range of skills and capabilities that make it easy to perform a new task with few or no demonstration. So any context learning can be achieved in many ways. The first one is few-shot learning. So in few-shot learning, the model is shown more than one demonstration of the task to be performed at inference time. GPT-3 can achieve excellent performance without gradient updates when performing few-shot learning. So the example you see in the top right corner is few-shot learning when translating from English to French. So in order to translate from English to French, GPT-3 requires you to give at least a few samples, typically more than one, of how translation is done from English to French. After you have given it a few samples, GPT-3 can start translating from one language to another. You don't have to fine-tune these things. You don't have to correct a data set of 10K samples of how, of words in English and French. You just have to give it few samples, few translation in English and French, and it can start translating right away. Another any context learning approach is one-shot learning. In one-shot learning, the model is shown only one demonstration of how the task is performed, and then after giving it one demonstration, the model can start performing new things. So in English to French translation example, you just need to provide only one example of how translation is done from English to French, and then you can ask the model to translate from English to French. Another really cool in context learning is zero-shot learning. So in zero-shot learning, the model can perform the task with only description of the task. So you don't need to provide any demonstration. You don't need to provide any single samples. So in zero-shot, for example, when translating English to French, you just don't provide any sample. You just ask the model, hey, can you please translate cheese to French? And the model will be able to do that without requiring you anything. So this graph shows the performance of different any context learning approach and how they perform according to the model size. So you can see that zero-shot learning improve linearly with the model size, but few-shot learning improve rapidly. So the bigger the model, the better you are going to the bigger the model, the better the results in few-shot or one-shot learning. So the performance of all in context learning approach, either zero or one or few shots, generally increase with the model size, which does suggest that large language models perform better. But it really makes sense that few shot learning give better performance than other learning approach, because if you can give models the few samples or few shots, then you are giving it the context of things before you ask anything. You are giving it a clue of what you want to ask it, and then it doesn't have to search wide. It just have information to start from. You might know ChatGPT. I think nowadays everyone knows ChatGPT, even if you are not into AI. So large language models are zero-shot learners, and I think ChatGPT demonstrates that through well. So if you ask ChatGPT, for example, what is the category of this news among the four given categories? So you say categories are sports, politics, finance, healthcare, and your news is Argentina is the winner of the World Cup 2022. ChatGPT is able to recognize that this particular news would fall under the category of sports. And just for you to know, ChatGPT, as the model itself says, it was trained on data before 2021, so it doesn't know anything about Argentina winning the World Cup 2022. But it can still able to recognize that this news fall into the category of sport. If you also ask it to complete the missing words, this would be a trivial task for most language models, but it does show how large language models are just short learners. So if you ask the model GPT-3, if you ask Chat GPT to complete the missing word in London is the capital city of, you can see it does it well. It can recognize that London is the capital of England. But this is a trivial thing for large language models to say London is the capital city of England. But again, that show the zero-shot learning ability of today's large language models. So now that we've been looking at large language models, which is actually a fascinating topic nowadays, let's look at implementation of transformers. So the original transformer model was implemented in tensor library, which is in TensorFlow, but it's deprecated now and has moved to tracks in JAX. So below is how you can perform machine translation inference from English to German with tracks. It's pretty simple, pretty straightforward, and it is very fast when using GPU. So the first thing is you create your model, your transformer model. You can choose the input vocab size you want, the dimension of the model you want, but this does look like a normal vanilla transformer. 6 encoder layers, 6 decoder layers, dimension of 512, and feed forward dimension of 2048. This is dimension in the feed forward layers. And then the next step is to initialize this model using pretrain and weight. And then the next step is to tokenize the input sentence. So our sentence is transformer is the universal deep learning architecture. After tokenizing this sentence, then you decode from the transformer. And then after you detokenize to get the translated sentence in German. So the translated sentence, I tried to put this translated sentence in Google Translate, and it does actually get it well. Like it's also translated back to transformer as universal deep learning architecture, which I think is amazing. Given that all of this thing is matrix multiplication, but it's fascinating that the model, by just using attention, the model can be able to do like machine translation really well. So transformer is now implemented in modern deep learning framework as a layer like other neural network layers. So PyTorch, Keras NLP has building block of transformers. So it used to be that to use transformer, you usually had to implement it yourself. But today you don't need to implement it from scratch. So you can just call it like other layers. In PyTorch, you have many building block of transformer. There's whole transformer, NN.transformer. You can load transformer encoder. You can use transformer decoder, and you can use NN.transformer encoder layer as a single encoder layer. And also Keras NLP, like we said, has many building block of transformers, from transformer encoder, decoder, positional embedding, sign-up positional encoding, and starts in packer layer, multi-segment packer layer, multi-head layer. So like all these frameworks, they are starting to incorporate these recent state-of-the-art models as layers to make it easier for developers to use them. JAX also has some layers of transformer. So if you look at Flux, which is a high-level neural network API in JAX, provides implementation of transformer block. Hugging face transformer is So Hugging face transformer is one of the popular implementation of transformers, which provide pre-trained weight of most models in NLP, computer vision, mid-model learning, and beyond. So if you really want to use transformer, I think you can't go wrong by using Hugging Face transformer library. So they make it easy to do tasks like text classification, question answering, summarization, text generation, and it is easier because it does take few line of code to download the model and to use it. You can also use models from other people. You can use models from this large research lab, and it's very easy to perform inference on a wide range of tasks using a Hugging Face transformer library. So by just creating a pipeline, specifying the model and the task that you want to perform, you can perform inference pretty easily. This example you see here is when you are performing sentiment analysis. You can do it in less than 5 lines of code. So you just have to provide your sentence. Let's say your sentence is transformer is a remarkable network architecture. After that, you create a pipeline for sentiment analysis, which you do by specifying your task, sentiment analysis, and choosing the model that you want to use. And then you apply your pipeline to your sentence. You can see that this model actually does figure out that transformer is really a remarkable network architecture. Like, it's positive. Transformer is a remarkable network architecture. So another notable implementation of transformer is Mini GPT by Andrej Karpathy. So most implementation of transformers, in particular GPT, are very complex. But Karpathy tried to implement GPT in about 300 line of code. You can check it out on his GitHub account. But it's one of the famous implementation of GPT. X Transformer by Phil Wang, known to Lucid Brain on GitHub, is also one of the famous transformer implementation, which is open source. So X transformers contain bunch of transformer models, and he keep updating this package. So if you really want to use transformers, I recommend you to use one of these open source implementation. So now that we've been looking at transformer, so now that we've been looking at transformers and large language models, let's look at the state of transformer today. So transformer have really become the universal architecture. So with few modification or without any modification at all, the same architecture is applied on almost all modalities. In NLP and speech recognition, people use transformer as arrays. In computer vision, people are starting to use transformer as arrays. In multimodal learning, people are using transformer as arrays. So back to computer vision, for example, so transformer take a sequence of token. But in computer vision, it could be a sequence of image patches. So in multimodal learning, it could be a sequence of different modalities that are jointly added together. In graph machine learning, people are using transformer, the same architecture. In robotics, people are using the same architecture. In reinforcement learning, people are using the same architecture. And thanks to Lucas Pair for inspiring this slide. Let's now look at efficient transformers. Transformers have proven to work in many fields, but they require excessive amount of compute and memory due to the quadratic time complexity introduced by self-attention. They call that self-attention has quadratic time of complexity because each token has to attend to all other tokens. So with such compute requirement, the application in raw bagged device are very, very limited. There has been many attempts to improve the efficiency or memory footprint or computational cost of transformer, which resulted in a zillion of Z-formers. But surprisingly, most people still use vanilla transformer introduced in 2017, the one that we've been learning. So there are many taxonomy of efficient transformers. People call them efficient transformer, but they don't work well, especially when you evaluate them the way you did evaluate original transformer. These new Z-formers, they might work well in one particular task, but they can generalize to other tasks. So you can see that on this whole taxonomy, some models really try to achieve linear time complexity. If you look at Linformer, for example, if you look at linear transformers, if you look at big parts, random feature attention, if you look at Perceiver, it also has linear time complexity. So people are trying to design efficient transformers by trying to reduce the complexity of self-attention, but it doesn't, like most of these new models which claim to reduce such time complexity, they are much slower than vanilla transformer, and they are rarely used in the practice because they don't have the same universality as original transform. So the other efficient transformer, I think that the ideal Z-former or the ideal new transformer should yes reduce the quadratic time complexity of self-attention, but it should be universal, and it should maintain the same performance across different tasks and modalities. Also, the ideal Z-former should not trade off speed for memory. It should not be hard-coded. Most of these new Z-formers are very, very hard-coded, and I think that's why they are not universal. So, and a really ideal Z-former should be simple and elegant. So the vanilla transformer is really simple and elegant. So it's this attention mechanism, and we saw that attention is just two matrix multiplication. So it's a dot product of query and keys applied to softmax and then multiplied to values, and you are done. So if you really want to learn about efficient transformers, I invite you to read Efficient Transformer Survey by people at Google Research. And the nice thing about this survey is that it is continually updated, so you can hope that by reading it, you are getting a decent overview of efficient transformers. So before we get to the end of this video, let's look at this amusing tweet from Andrej Karpathy. So he posted in October 19. The transformer is a magnificent neural network architecture because it is a general purpose differentiable computer. It is a general purpose differentiable computer. It is simultaneously one, expressive in the forward pass. Two, it is optimizable via backward propagation and gradient descent. And three, it is efficient, a high parallelism compute graph. Transformer is expressive because its message passing like architecture is general. It is complex and powerful. It is efficient, and it is able to cover many real-world algorithms in a small number of compute steps. Two, transformer is optimizable because of residual connection, as we saw, because of renormalization, and because of softmax attention. Absence of any flat tail, nothing complicated in transformers, just no flat tail. Residual connection support a kind of ability to learn short algorithm fast and first, then gradually extend them longer during training. I think this might be connected to where we saw the residual connection carry in position information to higher layers. And three, transformer is efficient because the compute graph is shallow and wide, mapping significantly better to our high parallelism compute architectures. Think about GPUs. An era attempt that understood the significance and optimized for this property was the Nero GPU paper, which you can read. So its success lies in the single architecture that is simultaneously satisfies all of these properties. Dodging attention is all you need paper is a bit haphazard and understand the magnitude of these insights, their history and motivation, but there are a lot going on. So I probably would have called the paper something like Transformer, a general purpose efficient optimizable computer, and presented it along the Neural Turing machine, Neural GPU, and friends, then applied it to translation as example. Something like that, but okay. Thanks for this amusing tweet, Karpathy. And thanks for all you are teaching. So let's summarize all we have seen. So we've been looking at transformer, we've been learning the transformer architecture. Transformer is inarguably one of the greatest inventions in the last decade in AI research and maybe in computer science as a whole. So self-attention is the key element of transformer architecture. The idea of using attention is to give the network the ability to attend to the most important part of the input data. So in the language perspective or the language context, the idea of using attention is to attend to the most important words. Other elements of transformer are material perceptron or feed-forward, as shown in the architecture, area normalization, and residual connection. And transformer was originally introduced for machine translation tasks, and it's quickly expanded to other modalities. So we saw that the same transformer architecture is used in speech recognition, the same transformer architecture is used in vision, the same architecture is used in reinforcement learning, the same architecture is used in robotics, the same architecture is used in multimodal learning. And finally, in the capital words, transformer is just a magnificent architecture. It is a general purpose differentiable computer. So if you want to dive deep into transformers, or if you want to do some practice, I have there some link for you. So you can go to the first link and then try to read, understand, and learn code in the tutorial. It is on PyTorch. You can also try to fine-tune a pre-trained BERT on IMDb reviews using transform library. So you can use this tutorial on Hugging Face. It should be fast, but you have learned many things by trying to do it. You can also skim over the annotated transformer blog post by Hang et al. So we use this annotated transformer blog post in some slide in this video. And that's pretty much it. Thank you for your attention. If you have enjoyed this video, please let me know. If you have any comments, let me know. And I can't wait to keep doing videos on some really hot topics in machine learning and AI research. Thank you for your attention, and please subscribe.